Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our first regular academic video on this newly launched YouTube channel under title Quantum Mechanics by Rajpura Abdul Wahid Bhatti. Okay. In this video, we are going to solve a problem of quantum mechanics which has been selected from the book Quantum Mechanics by Nordine Zetley. Okay, Nordine Zetley. We will follow this book as well as a book of Stefan Gasiorowicz and John S. Townsend. Okay, we will follow these three books. Okay, first we come to its statement. Okay, when two ultraviolet beams of wavelengths lambda 1 equal to 80 nanometer, nano standing for 10 raised to the power minus 9, okay, and lambda 2 equal to 110 nanometer fall on a lead surface, they produce photoelectrons with maximum energies 11.390 electron volt and 7.152 electron volt respectively. Part A, estimate the numerical value of the Planck constant. Okay. Part B, calculate the work function, the cutoff frequency and the cutoff wavelength of lead. Dear students, in this problem, two sets of values are given. Okay, lambda 1 and k1 and lambda 2 and k2, and we have to find the value of Planck's constant h. Actually, value Planck constant is given in tables of physical constants, but actually we have to confirm that our calculation reaches approximately close to that value. Okay, moreover we have to find out the work function and cutoff frequency and cutoff wavelength. Okay, now we move to its solution. Dear students, in addition to this solution, we will also consult a table of physical constants, okay, from which various values might be used in this problem. Okay, solution. We know that h nu, this symbol, Greek letter is called nu. Okay, usually symbol nu and symbol phi perhaps are similar. Anyhow, this is nu symbol. Okay, its capital case is capital N and small case is this V like symbol, h nu. Okay, we know that h is Planck's constant and nu is the frequency. Okay, we know that h nu equal to hc over lambda because frequency and wavelength are inversely proportional to each other and are inversely related. So here nu is equal to c over lambda, where c is the speed of light. Okay, and lambda is the wavelength. Okay, nu is the frequency, lambda is the wavelength, h is the Planck's constant, c is the speed of light. H nu equal to hc over lambda equal to w plus k. W is the work function and k is kinetic energy. Okay, this implies that we can rearrange this equation as k equal to hc over lambda minus w, equation number 1. Okay, where h nu is the photon energy, in which h is the Planck's constant and nu equal to c over lambda is the frequency of photon. W is the work function of the metal and k is the kinetic energy of the electron leaving the metal. Okay, because dear students, we have been provided two sets of values. Okay, two ultraviolet beams of which two different wavelengths and two different kinetic energies are given. Okay, so we will reshape this equation in two forms, and then we will take a difference of these two, so that we may be able to separate Planck's constant H in this expression, okay, which we need to find out. Okay, for two ultraviolet beams, K1 equal to Hc over lambda 1 minus W and K2 equal to Hc over lambda 2 minus W. This implies that K1 minus K2 becomes equal to Hc 1 over lambda 1 minus 1 over lambda 2 equal to Hc lambda 2 minus lambda 1 over lambda 1 lambda 2 by taking LCM. Okay, this implies that if we keep H on one side, then it becomes equal to K1 minus K2 over lambda 2 minus lambda 1 into lambda 1 into lambda 2 over speed of light c. Okay, equation number 2. We will just put values in this equation number 2, and value of H will become available, okay, which will be very close to the exact value which is given in table of physical constants. Okay, using lambda 1 equal to 80 nanometer, lambda 2 equal to 110 nanometer, K1 equal to 11.390 electron volt, K2 equal to 7.154 electron volt, C equal to 2.998 into 10 raised to the power 8 meter per second in equation number 2. Okay, yes students, sometimes speed of light C is taken as 3.0 into 10 raised to the power 8. Okay, there is no difference whether we take 3.0 or 2.998, but because actually for the purpose of solution of this problem, we are following this table, which I am going to show in the end of this table. Okay, we are following this table of physical constants in which speed of light is given as 2.998. Similarly, value of Planck's constant H, which we have to determine, is given as this in two different different units, joule second and electron volt second. Okay, we will find out both, and we will see that both will be very closely equal to both these two. Okay, moreover, 1 electron volt equal to 1.602 into 10 raised to the power minus 19 joule. This conversion factor will also be used in this solution, in this problem. Okay. Yes, we were here using these values in equation number 2. We get H equal to this minus this. Okay, just simplification. We do not need to waste our time. Okay, using these values, okay, H becomes equal to this. Okay, this after just simplification here. Small n stands for nano. Nano means 10 raised to the power minus 9. Okay, and hence by putting these values in equation number 2, we get the value of H equal to 414.46 into 10 raised to the power minus 17 electron volt 6 electron volt second, which alternatively becomes equal to this. Okay, 4.1446 into 10 raised to the power minus 15 electron volt. Okay, dear students, the table which is given in this problem at the end, from this table we can see that value of H in terms of electron volt second is very close to this, very close to this. Okay, so we have successfully found the value of Planck's constant H in terms of electron volt second. Now we will also find its other value in terms of joule. Okay, for this purpose we will have to use a conversion factor. Okay, this is the conversion factor. Okay, we know that 1 electron volt is equal to this so many joule. Okay, this conversion factor has been taken from the table which is shown in the end in the last part of this problem. Okay, 1 electron volt equal to this. This implies that H equal to this into, in place of electron volt we have used its value. Okay, so this after simplification becomes equal to 6.63136 into 10 raised to the power minus 34 joule second. Okay, Yes, students, when we compare this value with the exact value given in the table shown in the shown in the last portion of this problem here. Here we see that our both values of Planck's constant H are very close to these two values. Okay, these two values are in terms of joule second and electron volt second. Okay, so we have successfully calculated the value of Planck's constant H not only in terms of joule second but also in terms of electron volt second. Okay, so our part A has been successfully completed. Now we move to part B. Part B, work function W is equal to Hc over lambda 1 minus K1, equation number 3. Similarly, equation holds for second set of values. Okay, because we are provided with two different wavelengths and two different kinetic energies, so these two sets of equations can be formulated, and these have already been formulated in the starting portion of this problem. Okay, we will use both. Okay, and we will see that result of both is very close. Okay, actually equation number 3 is as exactly valid as equation number 4. We do not need to use both equations, but we are just using both these two equations in order to confirm whether our calculation is close to one and other. Okay, otherwise calculation according to equation number 3 is quite sufficient to solve the problem, but we will solve by both 3 and 4, and we will see that both values are close to each other. Okay, so first we come to equation number 3. Work function W equal to so and so. We have just put values of Planck's constant and speed of light and wavelength given in the problem. Okay, and this becomes equal to 4.11 electron volt. Now we come towards equation number 4, and we will see that this value is also very close to this value. Okay, this is 4.11 electron volt, and equation according to equation number 4, work function becomes equal to 4.096 electron volt. Okay, so 4.11 electron volt and 4.096 electron volt both are very close to each other, and so we have successfully calculated the value of work function W. Okay, now we come towards mu naught, that is threshold or cutoff frequency. Okay, we know that mu naught equal to work function W over H is called the threshold or cutoff frequency of the metal. So mu naught is equal to work function W over H. By putting the values, we get the value of mu naught, that is cutoff or threshold frequency, becoming equal to 10 raised to the power 15 hertz. Dear student, hertz means 1 over second. Okay, hertz and second are reciprocal of each other. Okay, hertz mean 1 over second. Now lambda naught, cutoff wavelength. We know that wavelength and frequency are inversely related through speed of light c. Okay, lambda is equal to c over mu, and similarly lambda naught, cutoff wavelength, is equal to speed of light over cutoff frequency. Okay, so by putting these values, we see that lambda naught becomes equal to 299.8 nanometer, and this is approximately equal to 300 nanometer. And this is the end of our video. This is the end of our first problem of quantum mechanics. Till next video, Allah Hafiz.